Welcome to this code walkthrough stream of Moose Miners. I'm just gonna start with showing why I'm doing this one. It's to promote my new game, Moose Diver, which is releasing on Monday. So make sure to add this to your wish list or try out the demo. Until then, and if you're watching this as a VOD afterwards, then maybe the game is out and you can buy it. Yeah, let's see. There's a few viewers here already. So I'm gonna start with just starting the game in case someone hasn't seen the game before. And so let's see. I hope everyone can hear me. I've seeing some activity in the chat at least. Oh, started the wrong way. Just give me a second. I'm currently working on an update and some things aren't done yet, so I have to start it in a way directly into my prepared save file. So let's see. Yeah, so this is Moose Miners, and yeah, you have these moose. They can have these saw blades, and they mine gems and bring them to. Yeah, this is quite far along save file. I played about 8 hours in this one, and they deliver the gems into these mine carts, and then they end up down here and gets processed and combined with sticks to craft wands that are then sold to get more money. And down here there's a forest, and it's the same thing here but with trees instead of gems, and you can upgrade the different some different attributes on the moose, and buy new rail. And when I zoom out, I have this map view, so we can zoom out really far and look at the big base. Yeah, that's pretty much the basics of the game. And there's a bunch of upgrades here. This game is already out and available on Steam. Links are in the description for both Moose Miners and Moose Diver, in case you're interested. So let's head into the code. Let's see, I'm just gonna okay, so here we are. Let's start. I'm just gonna go through the program pretty much from top to bottom, and do some dives every now and then. So let's start with in the main method. This is a game written in C, and I'm using Raylib to help with things. It's a really great game library, highly recommended. So yeah, this is just some test code I've commented out, and some argument handling at the start. Nothing special there. Yeah, I do have a profiler, but maybe if someone is interested in a profiler, we can take a look at that later. So many objects on the screen, isn't your computer about to explode? Yeah, feel free to ask questions in the chat as well, and I will answer them as I see them. yeah, you can. The game can handle quite a lot of objects on the screen at once. Performance has been a major focus for this game. It's sort of the selling point. I wanted to have a lot of things happening at once. Would you say Raylib have done a lot of the heavy lifting or mostly helped with boilerplate? Raylib has mostly helped with boilerplate, like handling the whole window stuff, creating a window and like input things with the keyboard and mouse, and this game hasn't gamepad support with my other games. Gamepad support in Raylib has worked well as well, and connecting to OpenGL with some helper functions and things like that. I mean, Raylib is really lightweight, so you have to write a lot of things yourself for the actual game logic. Let's see. Yeah. Yeah, just some setup here at start, and yeah, here the Raylib things start initializing the window and things like that. Not that interesting. Nothing special there. And I'm doing some shader setup here. Some of these setup things are a bit of a mess in this project. I never bothered to actually clean it up properly. But that's how a lot of real games actually look like under the hood. You focus on getting the game out and getting new stuff out, and some things get to stay a bit messy. It's fine. Let's see. Loading some settings, updating the language, and this game this is my first game I've released with localization. Let's see. What difficulties have you encountered when working with 3D with Raylib? There hasn't been that many difficulties other than some 3D is a bit difficult sometimes, struggling with camera math and things like that. But that doesn't have much to do with Raylib. And OpenGL is it's just a learning experience with all those things. There isn't any particular thing that has been extra difficult, I would say, with a 3D. It's just another dimension compared to 2D, and rendering APIs are 3D anyways, so and loading models instead of only textures. But yeah, it's been quite straightforward, especially the Raylib part. Yeah, and as I said, this first game with localization, and for that I just have all the strings in the game are just like string constants that are updated based on what language is selected, and it's nothing more fancy than that. And then loading some fonts. Some of the fonts are different for the different languages, and I have different sizes preloaded from TTF files for the different font sizes we use in the game. And then just some UI setup. And oh yeah, let's get back to here. And then the settings system just uses the like a save storage value thing that Raylib had. I'm not sure if it has it anymore. I copied it out. It might be deprecated. I'm not sure. But it's just a very simple thing with that just stores ints for settings or floats. I added a special one that stores a float. And the init data is not, let's see if there's anything interesting here. Load textures. Yeah, let's look at the texture loading, because that one is updated since Sidestep Legends. I did a stream like this for Sidestep Legends, the game I made with Ready before this, and in this game I made a more proper loading screen that shows how much resources there are left to load. You saw it when I started the game before. So for that I just have this load queue item, which has a target pointer and a path and some parameters and a load function. So for example, this one queues load texture with mip maps, and then this is just added to a queue, and then later in the main loop I load a resource and then render a frame, then load a resource. We can take a look at that. Loading. No. Okay, where am I? Wrong file. Okay, here. Update loading screen. So when the game has started rendering, I call we start up in the loading screen state, and then we do this load next item that checks if there's anything left in the queue, and if there is, it loads it with the resource chunk system. This is the RES thing that Ray made, the guy behind Raylib. It's a resource asset management thing, which it's really straightforward and easy to use. And that one, I think I talked about that one in more detail in the Sidestep Legends code stream, so you can watch that if you want. This one just loads the resource and returns true if there's still if it loaded the resource. If there's nothing left in the queue, it returns false, and then we're done. And we try to load as many items we can in 33 milliseconds, just to keep a steady frame rate during loading, so we can draw the text update. And the reason I'm doing it like this on the main thread is that OpenGL is very single threaded, so you can't really use the OpenGL context from other threads without messing around a lot. It's not really meant to do multi-threading, and a big part of loading resources is creating like the textures on the GPU. So this was the easiest way. Otherwise, a more straightforward way would probably be to just do the loading on a separate thread, and then have the main thread worry about rendering how much of the loading is done. But OpenGL doesn't really work like that. So that's how the loading work, and yeah, a lot of setup with the lighting, thing. Have a really dumb lighting system that I should probably make a bit easier, but I basically have a sun light struct for each shader I use in the game. So it gets becomes a lot of boilerplate code for this, but it's fine. And yeah, that's pretty much it here. Yeah, and then we come to the actual main loop of the game, which is just it's just a while loop. That's how the Raylib applications works. Most applications work this way, which has a main loop. Just check if the window should close, and if not, you just continue doing what you're doing. And start by running Steam callbacks. It's like just to tell Steam that we're still alive and doing things, and handling some Steam events when needed. Updating the music. Let's see, and loading. We went through. I have some test states for different tests I've done on debugging, and then we get to the main menu. And the main menu is handled like all the UI menus in the game. It's an immediate mode system, so I just draw things like a background, and then we get to the buttons, and the buttons are just a function that returns true if you press the button. So this function is responsible for checking if the button was pressed, and it also renders the button. And hi. Getting some new people in the chat. Welcome. So first, just checking if mouse button has been pressed. This also actually has support for gamepad, even though this isn't used in this game. And check if that press was within the button, and then I have this control state, which it determines how the button should be rendered, so it can be rendered in some different states. So let's see. Yeah, and the actual button is texture atlas. Let's see, we can probably show that. I'm just gonna add a window. Here we have it. Yeah, let's have it like this. Doing some live layout changing. Let's see. I think I have some questions in chat. Wait, your build system is a bunch of bat files. Why not use CMake? Yeah, the build system. Yeah, we can take a detour on that a little bit. Let's hide this one for now. Yeah, just have a bunch of bat files. This is this build Windows with bat is something that that comes with Raylib. It's a simple build system. I'm not using CMake because I really don't like complicated build systems. They're really unnecessary. This game is just built from a single C file, so the core basic Windows C file, which is the one we've been looking at. In this, I just include all the other C files that I use in the project. So it's just a single compilation unit, and build everything like that. And yeah, it builds pretty fast. It's really simple. I remember the animal sounds were a bit annoying because they trigger every time you click on the shop or to upgrade. I'm wondering if that is, if you're talking about Moose Diver, because in most miners there's no animal sounds in the shop, it's just when you're placing the moose. Let's see, have you missed any modern graphics API feature? The other day, Raisin made an AMA and tons of people were asking for a Vulkan backend. Do you think it should be a priority? I don't think it's reasonable to port Raylib to Vulkan, really. It's not gonna, I mean, that type of interface is probably not gonna work very well with something like Vulkan. It would probably, in that case, it's better to just run OpenGL on top of Vulkan for compatibility reasons, which I have thought about doing, because OpenGL, I don't miss any features from the modern graphics APIs because I haven't really needed them, but OpenGL in particular has a lot of compatibility issues. I mean, yeah, the drivers in general is not usually not that good. I had for like a few months after Moose Miners released, the game crashed on a lot of people's computers that were using AMD graphics cards, some of the AMD graphics cards, because they had a driver bug that just caused a lot of OpenGL stuff to crash. So it's more like that. Issues like that, and there's some issues here and there, and if I wanted to do cross-platform, like Apple has deprecated OpenGL like a while back, and then I was stuck on an quite old OpenGL version. So, but in that case, I would probably just want to rewrite a lot of my rendering stuff for different APIs, and pretty much remove that part of Raylib and just use the other parts. That would probably be a better way to do it. Yeah, I don't like Vulkan at all. It's very complex, but I'm scared OpenGL gets obsolete on new hardware. Yeah, that's a worry I have as well. But I think it seems to be fine enough now. I'm feeling like Moose Miners has come to a quite stable place. Now I managed to fix all the known issues I had with it. And if it becomes an issue in the future, there are options to run OpenGL on top of Vulkan, or maybe even DirectX 12. But at least on Vulkan, I think. And I'm not sure how much overhead that causes, but from what I've read, it's not that bad. Let's head back to the button thing. And we so the buttons look like, so this is the drop down. Let's see, this is the button texture. Let's see if we can have login inspector. So it's a simple sprite sheet, and control state decides which one of these that is rendered. So that's how pretty much all the buttons A lot of the UI are made in the game, and then it's just texture is just rendered with one of Raylib's draw functions, and the source determines which part of the texture is rendered. So pretty straightforward stuff. And let's see how, main menu. If I can type. And that's the main menu pretty much, yeah. And then the other, the same save selection UI, it's made the same way. The leaderboard is made pretty much the same way. And then we get to the actual game, the playing state. So it's just a state here in this big switch statement. No need to complicate it. I have a lot of debug things I'm using while developing. Just a lot of different keyboard combinations. Using, quite heavily using if-defs to add or remove stuff depending on what type of builds I'm making. I'm making three types of builds. Debug builds, which is just a full debug, no optimizations on the code, good for debugging because you can see everything. Quite slow, because the compiler doesn't optimize pretty much anything. I also have all my debug options available in that. It's the build and run one. And then I have a release build, which is it's maybe a better name for it would be optimized, because it's not what I'm releasing. It's just an optimized build with debug info still, so I can still debug, but it's a lot of things are optimized away, so it's harder to debug. And I have all my debug options on as well, so I can cheat and stuff like that in game to try out things easier. And then production, which is what's actually getting released on Steam, and that one is of course optimized, but it also has all the debug options turned off, so that doesn't get included. And some more things are optimized away, like asserts and stuff. So for example, this is only available when not in the production build. With some debug options, and let's see. Some animation updates for the rail. It's a build animation for the rails, and this pretty much just updates the time and the numbers that are currently being animated, and also playing sounds if needed. Same with the minecarts. And let's do a proper deep dive on because now we're getting some tasks here. So the task system, it's the system I use for multi-threading things. So to get the performance I have in the game, it has to run on it runs on as many threads as there are cores, pretty much. I think it uses the cores quite efficiently, at least. And for that I have this task system, which is found here in the task runner. The actual task system is really simple, as you can see. It's just about a bit over 100 lines of code. And some initialization, and you add a task with this add task to queue function, and I have some modified versions that makes sure that waits for a spot if the queue is full, for example, or add the task in the first in queue if it's really important. But the queue itself is actually it's not stored here. So this is just a simple code file that just handles the logic. I can look at the queue. Queue just have an array of tasks and and the count and how many worker threads that the tasks system is currently using. And the task is quite simple. It has a function which is the actual code that's going to run. That function takes another function pointer, which is a function to run when the task is done, in case you need to, for example, you want to tell how many items were actually handled in this update and stuff like that. And then it's just some parameters, some data, which is just a byte array. We'll have a look at an actual task to see how that's working. We can take a look at this update visible trees transform task. So this is the task that updates the transforms for all the trees on the tree side, because none of the trees or gems are stored as they are shown. We can look into that in the more, but I have a video on the channel about that in a bit more detail. But let's focus on the task thing here. So each task has its own task params struct that actually says what the data inside the generic byte array is. So this task only has camera and the camera position. That's the only thing it needs. And just do a mem copy to struct like that from the input data to get it in the correct form. And then this task just runs a function, and this is the function that updates all the that calculates all the transforms for the visible trees. We can look at that. It's quite straightforward. It goes through. It gets the frustum rectangle, which is what tiles you can see right now with the camera. And so this just has. The frustum rect is just world space rectangle on what is visible, and then I'm just calculating the actual tile indices from that, and these are then a loop over those tiles basically. First the rows and then the columns, and let's see. And then here is the actual data of what trees exist or not, which is just an int array with the width of the world. So each tree or gem, the way it's stored is just okay. How far up that column has been mined. So that's why in game you can only mine from bottom to top on the gem side, and top to bottom on the bottom side. On the tree side, you can't mine sideways because there's no data that stores that, and that was an optimization I made to be able to have really large worlds. And from this, we just check so the current row we're in is actually there. It's not been mined, and if it's not been mined, then we can, based on the position, we can get like the angle and position offsets, so the grid isn't completely uniform. So it's a little bit. So this is just basically a seeded random thing based on the position, and then we get the color index, which we get from what type that tree should be, and this one is, yeah, that's also something I think I went through in that video. But it does some seeded random things here to figure out which, if it should be like a gold, diamond, or black ore, and if it's not any one of those, it's just whatever color it should be for that row, because every 25th row it changes to the next tier and just loops around. And there's also the magic colors for when you're deeper into the game. You have this magic aura around the trees and the gems, and we can get that from the row position as well. A lot of matrix multiplications to get the transform, and then it's stored in like pretty much most of the things I send to the GPUs. The GPU is stored as this float 16 v16, so it's 16 half floats, which is an optimization I made because sending data from the CPU to the GPU was one of the biggest rendering bottlenecks in the game. So by using 16-bit floats instead of 32-bit floats, I halved the data I need to send. And the precision was good enough because the game is, since the game is tile based in like a sense with all the gems and even the moose position and everything. They have like a grid position which is an integer, and then that is later converted to like a floating position for rendering. So there are never any big floating numbers sent to the GPU because everything is local to the current camera grid position, and then it works really well with these lower precision floats. You can use them without seeing any glitching. So that is prepared like that, and this visible tree transform is just a big array with that's the size of the max visible rocks, and that's how many visible rocks that are supported to be shown at once, and that's just a number I set 32768 as a max. That was reasonable for the max zoom level. And for I also set the color and a magic hash, which I'm not really sure what that's used for actually. Right, don't remember. But all these are sent to the shader to render everything in an instanced draw call later on. And when that is done, we run the onTaskDone function, which also updates this integer, which is actually used as a boolean here, just to say that okay, the visual tree is updated, is done, it's ready for rendering. And then I have a wait on this later when drawing, to make sure that okay, it needs to be done before we draw, since this part is multi-threaded. So let's move forward. So all these are added to the task queue, and there was nothing else to show. We can just show a bit more. So the way the task queue then works is this run task is run on a separate thread, and it just has an infinite loop where it checks. Okay, can we get a task from the queue? And this one should check. Okay, do we have any queue tasks left? We get the next task in the queue and updates how many we have left and return. Let's see, return the result, which is just if it succeeded or not. And the task is stored in this pointer here, yeah. And then we get the task to run, which runs its function. And a function can also return true or false, depending on if it was done in that run. So you can have a task that goes over multiple frames or multiple ticks. I'm not sure if I ever use that, but that functionality is there. And if it wasn't done, then it's added back to the queue. And these while loops here are because add task to queue can return false in case we have more. Currently have queued more tasks than we have set, but this is a quite large constant that's it. So that pretty much doesn't happen in runtime, but just in case. And then and the same if we have to wait to get the task on the queue because something else is using it, then we just sleep a little while. And this whole part I think could be optimized quite a bit. It's something I'm probably going to look at some point to see if that's going to make any difference. I think a bit more time is spent in here than I want. Now we do some just update some camera things and set the shader values for the camera. It's a pretty standard shading model. So it just needs to have the camera position to calculate the lighting properly. And here we come to the rendering of. Oh, okay, yeah. The first part of the rendering, which is preparing the render data. We already did some preparing for the trees and gems. But then I do a lot of other preparing, which is run on the main thread still for now. I think they are fast enough to not cause that much of an issue. And yeah, all of these pretty much just look at this visible grid limits, which is okay. What grid positions can we see? Grid position is just 2D integer, which is the grid system, and then looks at the data for, in this case, the rails to and prepares render data for all the rail that's visible. And this also handles positions for animating if the rail is building currently and animated in. That's handled here as well. What you can see here maybe is like all this like the free arena stuff. So for the rendering code, I'm using just a memory arena thing I made. It's probably not the best implementation of one, but it has worked well enough for me. It just has an end capacity pointed to the data and also a boolean that says if it's allowed to grow or not. And can have a look at just the free arena. Yeah, so here's the arena allocator. It's also really short, just a bit over 100 lines. Have some things like ensure capacity. So this is quite similar to a dynamic array in a lot of ways. It just holds generic data. So these are pretty much as they would have looked in a dynamic array implementation. I have a version that's make sure that it's aligned to a certain alignment in case that is important. And here's the arena alloc method, which takes the arena and how much you need, and it just checks that okay, what's the current end of the so this is I want some new memory from this arena, and that memory could be and if the arena is big enough, it's just going to return a pointer to what it already has. So it checks what is the current end position of the arena, how much have we given away to other areas, and adds the amount you want, and checks if that is fitting within the capacity, and if it's not, then we need to grow the arena. But here we check if the no growth is set, then we just trigger a crash. Should probably just happen assert here or something. I'm not sure if we want to crash in the production environment, but yeah, that's. But this should only happen while I'm developing. Otherwise, I have a bug. And but if the growing is allowed, then we just allocate a new block of memory with a new capacity and copy over the old one to that and free the old one, and that's it. And after that, we can just return a pointer to the data pointer plus the end. And increase the end by the new byte length, and that's pretty much how that one works. It's really straightforward. and I use these for pretty much all my rendering data, which when I don't know beforehand how many entries I need, which is for most of these. So we have so we have the backing arena, which is temp memory, and then I have the transform, which is the actual thing I want, and that's what I'm allocating from the arena for this. So this is just the transform array that's going to be rendered, and that is used in here then later to so when we have calculated the transform matrix, we want to check if it's gonna fit in the current within the current arena, and if not, then we reallocate it, and then we just copy over the transform to the array. So that's and that's how pretty much all the prepare render data function works, with some modifications depending on what type of data, but that's the gist of it. So we can skip over these. Let's see what this one is. Oh yeah, this is the small effect, the particle effect when you have picked up a moose. So it's just updating a particle system with that one. And update minor animations. Yeah, let's look at this one. So yeah, all the moves are of course animated, and that is done with the animation system, or at least animation data that comes with Raylib, which is this model animation, and that is loaded from the model file. You get all the bone info, the transform, like the frame poses and things, and inside, and yeah, bone count, frame count, and everything. And you have some of the bone info is in the model struct. And so let's see here. So in here I have one animation data for each miner that can be, or moose. When I started the project, it was only moose miners, and so that's why the moose are always called miners in the code. And the loggers didn't exist yet. So each miner has its own animation data, and we get that for the ones that are currently visible, and update their animation state, so they have 4 different animations: walk, run, idle. Attack is the one used for the wizard moves when they are crafting. So they have a current animation and next animation, so we can switch between them smoothly. And we check the frame counter and just update the frame counter basically, and if it's reset it if it's gone over. Then we have a transition time where both animations are playing when we're transitioning from one to the other. And this is all pretty much all I'm doing on this CPU. Then the actual animation of the model is handled on the GPU, which we'll get to. Let's see, I think probably in here prepare minus rendering. So let's see. Minor render list. Yeah, so this one, yeah, we can look at that later. This is updated elsewhere. We have the minor render data, which is all the data needed to render it. And let's see if the animation is done here. Probably not. But at least here we're updating the transforms, and then we're sending them to the GPU, just updating the buffers here, since we don't want to do two draw calls for the game, one for the shadow map and one for the actual game. So we don't want to draw them directly here, just send them to the GPU so we can combine that buffer and just draw directly from it later. Let's see, I don't think there's any of the animation stuff here. Okay, render minus instance. Yeah, so after the buffers have been updated, this is run sometime later. One, as I said, once for the shadows and once for the actual game. So just some shader setup, and here we have some of the bone setup for the shader. Then I think here we have the anim index ID. Okay, frame index. Okay, yeah, so these, we have these buffers that are set somewhere. Let's see. Yep. Primers only for rendering. That's some debug stuff. Okay. Prepare minus render. Okay, so it is in here. So in here we have the animation stuff. So we bind the buffers for the animations. Then we have this one, which also is done in here. So we'll go through this for all the moves that are visible, and then we get the animation index from this animation data that we looked at before. That just returns which animation should be run, and then the frame index is stored in the animation data. The frame count is stored in animation data, and then these are all sent to the vertex shader for updating the animation, updating the vertices according to the animation. So we can take a look at that and see what that one's called. Skinning instance.vs. This is it. So this is a typical GLSL vertex shader, and in here we get all the animation data, and then the actual animation data in the for the game, for the animations are stored in the texture, which is this. Let's see. Yeah, this animation frames. and then I have some constants here that says how everything is laid out in the texture. And this texture is created on the CPU at the start of the game. It translates all the data from all the animation data into image data. And then it's just a matter of calculating the UVs to sample this texture from. Let's see, we have this. Yeah, so then I do a bunch of texel fetches for the translation, the rotation, and the scale, and the second one, because the animation is. The original animation data I think is at 30 FPS, and it can also be scaled in speed, so it can be slower and faster, and then I do interpolation between the frames, so it becomes smooth. So that's why we have two translations and two of everything. And these indices are calculated with some math, depending on how the texture is set up. So that's how the animation works. Then we can get back here. More preparing for rendering, and then we start the drawing. This is a Raylib function to begin the drawing. First we just draw like a demo text thing, which is for the demo wall. And that's the first thing we do. Then we do the render shadows, and this is a basic shadow map. It just sets up the camera settings for the shadow map and the shadow texture, and then I just have this draw shadow casters, which has calls to all the render functions that should cast shadows, which is a bunch of stuff. Most things in the 3D world cast shadows. Not that common. That's nothing special there, really. Then I have my own extended. I've done this quite a lot with the Raylib stuff. It's a really good thing about Raylib, that the code is so easy to read and modify, and sometimes I find that I need some functionality that's not really provided in the standard interface. I just copy over a function and edit it. So this one is extended. I think the original begin mode 3D didn't allow you to specify the near and far plane. I think they were set as constants. So I think that's the only modification of this one, pretty much. And then we set some shader values for the lighting, render ground, and the ground is a bunch of different, so the ground changes as you get further away from the base, and that's what all this is, and then it has a smooth transition and things. So it's just two big quads, which renders different textures and transitions between them, basically. And then there's different lighting in the different areas and stuff like that as well. Render rocks. So this is what, yeah. So this is where we render the gems, and the trees look the same. And here I also have my own version of a Raylib function. The one included in Raylib was draw mesh instance. I needed some more stuff, so I just copied it and added my things. This one sends the color values to the GPU as well, and it don't transfer transforms. That one means that the transforms are already on the GPU. In the standard draw mesh instance function, you send the transforms as an array in here, and it copies them over to the GPU and binds them and then renders. But because I have the shadow map thing, that becomes quite inefficient. I don't want to send the same data twice. So that's what I did before when I bound the buffers and everything. And here I just need to send BBO IDs for the different buffers. In this one for the transforms and this one's for the colors. And then I can just bind them here for the rendering. Let's see, I think I've got a question. How do you handle 3D animation blending? Yeah, I went through that a little bit, but I can talk a little bit more about them. But it's this part. Or you meant blend? Yeah, I think actually in this game I'm probably not blending between the animations, because usually you're not looking that close at them, so I think I just didn't bother. But if I wanted to blend between animations, it's handled the same way as the blending between frames. So instead I would have to have a second animation index in here, so I can sample from another animation as well, and then have 2 additional values of everything. So we can blend first between the frames for each animation, and then we do a second lerp between the different animations. So that's that's how I would do it here. But in this game, it didn't really matter that much, so I didn't do it. I think I probably did it for Moose Diver, but that one is still. I think that one is rendering. That one is handling all the animation on the CPU, so it's not in the shader because I only have one character, and then it was fast enough to do that. Other than that, this draw mesh instance function is as the built-in Raylib one is just that it doesn't transfer any data from the CPU to the GPU, and it also handles a second buffer for the colors. Let's see the render rocks, and then we also have the magic sort of aura around the gems, and the trees are just a separate render path, pretty much, with a separate shader to get that effect. Then we do some unloading, render group markers. I think that's just, these are the flags for the the flags for the mining, the moose groups. On render miners, I think we looked at this one a little bit. Yeah, maybe we didn't. And this is pretty much the same. There are a bunch of passes here for different things. We have like different 3 different miner carts passes, one for each one for each normal miner card, and then a bunch of passes for the sci-fi render cards. That you just handled in separate separate draw calls here. I also have this LOD system. It's really simple. I'm just looking at, so the LOD can be controlled by either the graphics settings. So if you have set to a lower graphics settings, it's gonna use a worse LOD, even if you're close. But if you're on high, then it uses the get LOD level, which just looks at your current resolution and compares that to the zoom level and decides a LOD level based on that. And that's just that's how it works. And then I have a bunch of these functions that returns the correct model for the current LOD for everything that should be rendered. In this case, you get a cart model, and you just render that for everything. So each, so it's all or nothing with the LOD in this, because it's a top-down game. It works pretty well. That when you zoom out, you just switch all the models to a lower LOD when you zoom out. If you would have like a game where you're on the ground and you're looking like a third-person or first-person game, then that would obviously wouldn't work very well, because different things are going to have different distance, a different distance to you. So you wouldn't want to. You can't switch like. But that's a benefit of having a top-down game. That's where everything is pretty much the same distance from the camera. And this uses draw mesh instance, no data transform, and just as the other one, this is just a simple modification to the draw mesh instance function in Raylib. And this is just as the other one. It doesn't have to transfer the data because the data is already transferred. But this only has the instances and no color values. So it just sends just renders the like that. And there's a bunch of draw calls for the different parts of the moose, like the moose itself, the carts, the helmet, and the saws, and jet engine and skates if that is unlocked, and things like that. So let's and then just need to unload. Okay. And more rendering things, pretty much set up the same way. They use the prepared render data and rendering with the instanced calls. Then renders particles. It's just for the particles when you picked up a moose. Render grinders, compressors, balance card. And that's pretty much the rendering. And then we have, so let's see. Okay, so that was the rendering for the normal 3D world. But if you zoom out, you end up in the map view, which is handled quite different, because that's like a 2D view representation. I'll show that when show the game at the start. But if you play the game, you know exactly how it looks like. It's just rendering squares. Like it's just exposing the grid system of the game basically, and rendering a square in the grid position for where everything is. So a moose is like a green, blue, some color of a square that moves around in the grid system, and you can see colors for the different gems, and and things like that. Have you had any weird OpenGL issues while using Raylib? Yeah, a few, I think. There was something, yeah, some shader didn't work at some point because I did something that Intel, for Intel GPUs, but that was before release. I did something that should be legal in GLSL, but Intel didn't support it. So I think I was like editing a value that's also an input or something, and that worked. That's a typical thing that can happen. Different drivers are what would you say? Like the different drivers are have differences in how they interpret the specs, I guess, or bugs. But the main one I mentioned before was that the game was crashing on a bunch of AMD GPUs for a while due to an AMD driver bug with their OpenGL driver. That was an annoying one, and I've had for a very long time I had what was called at the Steam discussion board. People were calling like the yellow screen, which basically was that nothing was rendered from the 3D stuff. You only saw like the clear color, which happened to be a yellow color. That was an issue I had for a long time. A few people had it, and I didn't really get much data from them to figure out. But after like a few months ago, I think it was this summer, I finally figured it out, and it was a bug in NVIDIA's driver. So NVIDIA has a thing called threaded optimization for OpenGL applications. So as I mentioned before, OpenGL is very single-threaded, but I guess NVIDIA decided that we want to make it better by making it multi-threaded in our driver. So they have an option for that. That's, I think, usually is turned on by default by their driver, which tries to run OpenGL calls on several threads, basically. So so they can go about quicker, and that of course had bugs. So in my game, and I think some other person had some issue with some Raylib example with this as well. It's caused the yellow screen issue for a few people, and so then I had to I can show what I had to do to fix that. So I have this NVIDIA fixes C file. So NVIDIA has an API to like edit profiles for games. So it's pretty much like the profile you can see in the NVIDIA control panel. If you open an application, there's a bunch of settings you can turn on or off in there. So you can edit a more a version of that has a bunch of more options, even though this option exists in both. So yeah, whenever the game starts, it looks like tries to initialize this API, and if it succeeds, it's probably then it's running on the NVIDIA GPU, and then I'm looking for a profile for the game, and if it doesn't find one, it creates one, and if it finds it, it modifies it by setting this threaded optimization setting to off, which solved the issue with the yellow screen. And while googling this, other people had like issues that the performance of their application went to shit with this threaded optimization thing on, which is quite ironic. So I wasn't the only one having issues with this. But that's So that was that and the AMD crashes was the biggest OpenGL thing. So I had some issue with vsync at some point as well, but I think that was the GL. What's it called? WF, like the window management library that Raylib uses in the end. Let's see. Yeah, GLFW. I think that was due to an old version of that one that caused vsync not to. They had a bug in an older version, which was the one Raylib was using, which caused vsync didn't vsync at all for when you were running in full screen on some NVIDIA GPUs. So it locked it to 60 frames if that was the refresh rate of the screen, but you got a terrible tearing line like in the top middle part of the screen, like right across here. So that wasn't a really good experience. But that was just a bug in that library, some Windows exclusive thing. So let's see. Yeah. So let's get back to the map thing. So yeah, when you zoom out, it switches to a 2D version, and this is also divided into a prepare step and a render step, just as the other things. I like to do it that way. And this one takes what's currently visible in the visible grid limits, and it's gonna fill this map render data, which is a bunch of render passes. These render passes are basically either they are just a list of grid positions, which is gonna render a small grid-sized quad for each position in that list, or it can be these rects, which is just a rectangle that it's a vertical rectangle, so it's on this position and it has a length that grows up or down. So that's how the data for the map is working. So this just goes through all the different stuff that should be rendered on the map and sets up these positions for those. Let's see, yeah. So it does this for grinders and saws and storage points, wands and rail and everything, except for the gems and trees, because that's the part that I a little while back optimized, because that was really expensive to. It was really expensive to calculate like the type of the rocks and of the gems and the trees based on the seed for that many. It was fine. It is fine in the 3D view when it's not too many, like max 30,000. But in this map view, when you want to zoom out a lot, it can be like a few million at least that you want to calculate for, and then that became too expensive, so I had to cache it. So that's what this is doing. It's in this get gem chunk. It checks because we have a cache, texture cache. So I divided this rendering in into texture blocks of, I think it's 64 by 64 tiles or something. And then I can cache those. So it checks if there's already in the cache, then we can just return that cached quad and be happy. If it's not in the cache, then we need to generate that chunk. And here here we do we get the rock types, and as you can see, I've already optimized this a bit, at least with some CMD instructions, and then I did before this optimization to have it run quick enough at all. So you can see this beautiful intrinsic CMD code. That's how it looks when you write it. Honestly, I would very much just prefer writing this in pure assembly rather than these weird names, because the actual assembly instructions are much clearer. But yeah, there's no good way to do in this. Yeah, the Microsoft compiler, the Visual Studio compiler that I use, doesn't support inline assembly, so it wouldn't. I wouldn't be able to have it inline like this. I would have to have a export as separate function and a lot of hassle. So yeah, I'm just I'm running it with intrinsics instead. Yeah, I'm not gonna go into how this code works in detail because I barely remember it right now. It's some tricky stuff. So let's yeah. But at least it gets the types and then stores those in this temp buffer that represents a chunk texture. It's just a 64 by 64 bytes array. So we put the color type. So the texture isn't actually storing. It isn't storing the actual color for the gem. It just stores the index, which is from 0 to 19 or something, and stores that as a color, like just a single what do you call it? Like a single byte for each pixel, basically. So we don't have to send too much data to the GPU. So we update this temp buffer, and then later here we use that temp buffer to update the actual texture. And the texture is a big texture at I think it's like 2K texture, and so I update an area of that texture with the chunk data. And then we can return this chunk cache thing, which is then added to the render pass for the trees and the gems. So these have a position and the UVs inside the texture. So that's what's pointing to that cached chunk. Yeah, and some other stuff. and how many, and how much they currently can hold. And that's it. And then for rendering, we just do this. Yeah, it's the same story as with the other render functions. It's just to render this map data instead, which sends this different data than the draw mesh instance. Usually, this one doesn't send transforms; it just sends an array of instance transform. And this actually does it just in one pass, because there's no shadows here, so we can just transfer and draw in the same function without it being any issues. And for the gems and trees, we use this one, which is just a modification of the other one. And no, this is a rectangle. Okay. Let's see if we can find the. This is the gems and trees, and this sends the grid positions and the UVs. And we can have a look at the shader for this one. Map textured instanced. Here we have the vertex shader. So the vertex shader is quite simple. It just calculates pixel position based on the instance position and the camera position, and a transform based on this. So this is for a 64 by 64 grid chunk, and some UV flipping. And then map textured. Yeah, this is the fragment shader, which is really simple, really. So here we have the actual colors for all the gems and trees. So this is just copied and converted list of the colors I store on CPU side. And then sample. We get the texture. This one, texture 0, is the color index. And we just we just multiply up that to get the actual integer value, which is the color index, and then we can index this constant array here to determine the final color. And the UVs are used to figure out where in the texture we should fetch, basically, where the chunk is. So that's how the map is rendered. Yeah, and render map was the one we were looking at. And then have some debug stuff to draw the shadow map. And then we have the UI, update UI. Yeah, we can have a quick look at this. It's not. It's pretty much the same everywhere. So, but this is the in-game UI. Does different functions to draw different things. So these are just information static things. We have this is the buttons on the top right. This is just as the buttons I showed before when going through the main menu. It's an immediate mode thing, so it handles the rendering and the state update inside here. And so if you click it, it returns. Yeah, and if you click it, it returns true. So you can act on the action. In this case, this is the info, so it sets the info box. It toggles the info box open boolean. That's how the buttons work. So this is just going through all the UI stuff in the game and updating and drawing the buttons. Here we have what's this round button? Oh yeah. So this is handling the side menu with the upgrade stuff. So we have a bunch of buttons, and then have some upgrade buttons associated with them. And then just draw and update the ones that are currently active. Yeah, and these are the minor group buttons. Yeah, I don't think there's anything more interesting in here. So that's the thing top to bottom on the render thread. As you probably noticed, there's nothing of the actual game logic in here. It was just rendering. That's because the game logic is running on a separate thread, which we're gonna look at now. Logic thread. So let's see. Prepare. This is called. Logic update. Yep. So here's where the actual game logic is running, and this has its own infinite loop, and this is just running the whole time the game is going. But if we're not in the game state playing, or if the pause menu is open or the game is paused, then we just sleep for a while here. To not take up much CPU time, and some setup variables at the start. Handles autosave here, so it updates. It's just updating if it the time since it saved last time, and if it's time to save, it queues a save task, which first it copies the save, like the actual data, memory that should be saved into a buffer, and this is if you have like the game stuttering, like dropping frames every once in a while, this is probably it, because this data transfer is quite large. The maps, the data for the game is quite big, so it can take, depending on your computer, your CPU, it can take a little bit long enough to drop a frame or two, or some more. But then the actual saving to disk and everything is done on a separate thread. Otherwise you would have to wait, and otherwise the game would pause for like half a minute or a minute or something. Maybe not that bad, but at least a few seconds, depending on the size of your map. Yeah, some hack fix thing. Let's see. Yeah, so the logic of the game is divided in this task system that I went through before. So here we have prepare minecart tasks. Let me show what this one does. Oh yeah, okay, yeah. So all of these are like divided into. So I have like a hierarchy of tasks. I have prepare tasks, which there's one for each type of entity in general. So this one prepares just all the tasks that needs to run for the minecarts to update in the game. So this just adds that prepare task to the queue, and then that task can run on a separate thread, and then we just keep going. This is updating the current money for the player. And while this is happening, while this is running, the minecart task is the minecart prepare task is running and adding new tasks to the task system to update the minecarts. And then we'll do the same for the crafter tasks. So we add that to the queue. So I have a few and then after that we wait for the crafters. So I know that just how I have laid out the data, that the minecarts and the crafters, those two, they can update in parallel without affecting each other at all. So all the updating for the crafters and the minecarts are running in parallel. But then we wait for the crafters to finish, because the next thing, the storage point task, that can't run at the same time as the crafters, because that's the dependency chain there. The crafters are depending on data from the storage points, because the crafters are loading gems and sticks from the storage points, and those two I don't want to run at the same time, because then we could overwrite data in a bad way. But then, so we just wait for the crafters to finish, then we start storage point task, prepare those, and at the same time, and after that we wait for the minecart to be updated. So the minecart tasks probably runs a little bit longer. So, but yeah, so we might need to wait for them here, because then we want to do the merged storage chest tasks, which are handling the storage chests, and those are dependent on the minecart tasks, because the minecarts load and unload through the storage chests. But the storage points, storage point tasks could run at the same time here, for example. And then we wait for the storage point. No, okay, yeah, the storage. Okay, the storage point task we waited for before here, and then we run the second pass, which is done because each task is. Let's look at this, and so in the prepare storage point task, we have these params. Okay, yeah, and yeah, so we have these storage point task data. And I've set a task memory size, which is 4 times 4096. This is which is 4 memory pages. So I just wanted to pick a memory page multiplier for the task memory. How many lines of code is the game? Yeah, I'm not sure exactly. I think it's probably a bit over 100k, somewhere around that. I haven't looked. I did count it at one point, but I don't remember. But it's in that ballpark. It's I think it's over 100,000. It's less than 200,000. Yes. So the memory. So the task size is set to be 4 memory pages to have some nice alignment there. And then I calculate how many storage points I can fit in one task based on this. So this is magic number here is just the byte count for all the entries in this struct. So a bunch of data in here that are needed to update the storage points. So we allocate that aligned in the storage points task memory arena. So we get the data for one task. So one task here is, I don't know why it does that. One task here is whatever that is, like a few hundred storage point can fit in one task. And then we update all the data needed, and this is so this is copied from my global data just to make sure that we're not editing any memory at the same time. It could probably, this copy could probably be skipped maybe, but I wanted to do that as an extra, just to make sure that make things a bit easier to not write to the same memory at the same time accidentally. So this data is completely and also you get memory data. You get memory that's only going to be used from a certain thread. This chunk of memory, like these 4 memory pages, are only going to be accessed from a certain thread, certain core, and I imagine that might help a little bit with the caching, hopefully. So we do one task for the gem storage point, one for the tree side, and we do this for all the storage points that are currently active, and if we have filled the task, then we create a new one, and we add the current one to the task queue so it can start running. And then it runs in this function, which this updates the storage points. It's quite a small function, but it does the transfer between storage points, and it also, I think that's pretty much what it does. It transfers gems or trees towards the middle of the base, and it also spreads them out between. So this is done for until we've gone through all the storage tasks, and then this prepare task is done, and we say how many total grinders, which is this one storage line for each grinder, and how many we handled in this task. Let's see. How long did it take you to become comfortable with game dev? I have 10 years of programming experience, and game dev is really hard. With trying for 3 months part-time. I pretty much focused on game dev like right from the beginning. Pretty much all my programming experience has been game dev or game dev adjacent. So I started programming like a little bit on my own, and like a few courses in high school. But then in university was when I started programming more properly, and went to like a computer science education for it was a bachelor and a master's of 5 years. And during that, I think pretty much every project that you got to choose to do something yourself, I ended up making a game. And then after university, I got a job at a company that made casino games for like land-based casinos, like physical machines. So I worked on the game engine team for that. Game engine, mostly 2D, because the games were 2D. DirectX. It started on DirectX 9, and then we ported it to DirectX 11. C# was the language for that game engine, and I worked there for about 4.5 years, and then I worked with virtual sports betting games and some casino games as well, and that was with some web-based games. Some of them were made in C#, that was transpiled to JavaScript, and some of them were made in Unity. And after like 1.5 or 2 years or something there, that's when I quit to start this full time, which I've been doing now for 3 years, I think. Yeah. So you can add up the years there. I think it's probably around the same amount of. I think it's close to 10 years of professional experience, and then some university programming and stuff like that before with them. But all of that has been games. So I'm not really. I've been comfortable with making games from the beginning because that's what I wanted to do. Then the technologies I've used have been a bit different. The first games I made were mostly in Java, because that was what we used in most of the courses at university. And then of course the C# and Unity stuff in my professional life. But yeah, picking up C and Raylib was it was really straightforward for me. I did do. You can see it on the channel. I did start a project in x64 assembly at one point, like a city builder game. I think that was really useful to learn the low level stuff. So after that, C was really straightforward when you know how everything works under the hood. Yeah, but yeah, game dev is. I mean, it is tricky. There's a lot of things to learn. Like the whole graphics stuff is. I'm not a very good graphics programmer, for example. That's one of the reasons my renderer is a bit of a mess, and not that easy to work with. For example, I just render stuff in order, and don't have any generic things. So for each new thing in my games, I need to add like all the steps for that, and because I haven't focused that much on that part. I'm more interested in the CPU optimization parts of things. So I'm not sure I can give you a more exact answer than that. I think getting comfortable with game dev is just start making games is the best thing, and using something like Raylib I can highly recommend, because it's a really good learning tool. You get a good amount of the OpenGL stuff at the start, and it's easy to dive into more and work more directly with OpenGL and learn all of that, and especially Raylib with C, because then it's also very easy to just copy Raylib functions and edit them yourself. You don't have to do any translation. and it's easy to just build Raylib together with the game, because that's what I'm doing as well. So I have the Raylib source very easily accessible, and I even made a few modifications to the actual, but that mostly in config files and stuff like that, so in reasonable places to the Raylib. Yeah. So let's go back to this prepare task. Task queue. And all of these are using the add task to queue wait for spots. I don't think I ever call this directly. No, because of course all of the logic tasks needs to be run. So if the queue for some reason would be full, then we have to wait, because we can't skip running a task. Then the game would start not working. We say how many we added in this on task done, or how many columns. How many we didn't add, basically. This is updated, so this holds how many storage points have been updated. So this is also incremented then when the actual storage point task is done. So we can wait to make sure that when this is equal to total grinders times 2, because we have 2 sets of grinders, one for the gems and one for the trees, then all the storage points have been updated for this tick. And then we do a second pass of these storage points, and I do that for a few other things as well, and that's because the task is divided in separate chunks, or of the whole line of the game, and then we have a few hundred. That's one task, and another few hundred. That's the second task, and so on. But the storage points are dependent on their neighbors, because the resources sort of flatten out. So if you have a big pile, then it should flatten out and spread to the neighboring tiles. That's the game mechanic. Then since the task is divided in these chunks, then there's no way to transfer to the tiles that are outside the chunk. So the edges of the tasks, the spreading wouldn't work in the edges of the tasks. So you have this pass 2 that goes through and creates a second task for all the edges. So it just adds a few storage points into each task. I think it's 3 to make them spread between each other as well. And so that's why I have the second pass. And then we'll wait for those, and also these chests. And then we can start the grinder tasks, and those work the same way. It's just different logic to update the grinders. And here we just wait on the grinders directly. There's nothing else that's running in parallel at the same time as those. But that doesn't mean that this is only running at one thread, because remember, all the grinders are divided into several tasks. So if you have a full width base, there's probably going to be maybe 100 grinder tasks or something that can be run at the same time. So there's always some work to do. Then we do a second pass for the grinders for the same reason, because those also spread out. And those at the same time we can start queuing up the minor tasks, and they have a bunch of different tasks for the logic. I'm probably not gonna go into those right now, because then we'd be here all day. But we can just have a high level view of them, like a minor position task that's updating the position, selected minor task updates minors you have selected. I think also if they're picked up, it's this is what's updating those. MISC task, which is pretty much everything else, which is up like mining and unloading and stuff like that is handled in there. Occupied is checking what gems and trees are currently occupied. And movement is updating the this is the minor cart movement. So this is updating the movement of if you have several carts behind a moose, then this is responsible for updating the position of the carts, so they go into a proper line. And for all the miners, we go through this, check their state to see which task should they be added to, add them to that task, and if that task is full, then add it to the queue and create a new one, and so on for all of this. So quite a lot of stuff there. And yeah, and after that we wait for the grinders to finish, and then we update the storage minecart, and that is just run directly here in the logic update loop. And the same with the balance minecart. Could probably split those two out and run these two in parallel, but I think the balance minecart is so cheap that it doesn't matter. This one actually takes quite a long time. I've spent some significant work on optimizing the update of this one. It's the loading of resources that's quite heavy. Also, and then yeah, just after that, and then we'll wait for the miners and everything, and do some achievements checking here after the particles. And then here we just calculate how long this should wait, because the logic loop is running at 30 ticks per second. So we need to calculate the wait time in case it's going faster than that. We don't want the game to speed up just because your computer is faster. That would be weird. Though I do have a speed up thing in my dev mode. That mostly just works until the base is on really large bases. It doesn't do much. But then we just wait the wait time, and this is the Raylib function that it's the same that Raylib uses to limit the frame rate. It works really well. It has some good things to handle different platforms, depending on what things you have defined in the Raylib constants configurations. And then calculate some frame time for the rendering, because this is updating 30 times per second, but the rendering thread can run as fast as you can render, depending on, if you turn on vsync, then it's going to sync to the screen. But a typical scenario would probably be the render thread is running at 60 frames per second, and the logic thread is running at tries to run at least 30 ticks per second. So that's a problem, of course, because the logic thread is updating all the positions and everything for all the moves and the mine carts and things like that. And if we were just using those positions directly, then they would just stutter. Then it would be like if they were updated, if the game was running in 30 frames per second instead, for example, or if the game is slowing down because it's too heavy for you, then it could be even worse. And that wouldn't be nice. It would just stutter. So I calculate some time since the last let's see, I think that this is the difference between the previous tick and this tick in like render time. So this can later be used to interpolate positions. So all the positions for let's see, we can go to minor positions maybe. Yes, here. So all the positions for everything that moves in the game. So for the moves and the mine carts and everything, it's double buffered. So the previous, so we have minor grid positions, for example, and prev minor grid positions, and each tick, this one is updated, this one is set to what this one is updated to the minor grid positions. The minor grid position is updated to the new position, and then when rendering, I interpolate between these two, which means that what you see in the game is actually at least somewhere between it could be as much as one tick behind what's actually currently running, but in this type of game that doesn't really matter at all, because it's not like a fighting game where you need to see the new position as quick as possible. Here it's completely unnoticeable. But that's how that is handled. And if I were to redo the whole game now, I would probably redesign something so I could have the tick rate much lower, because the tick rate of 30 per second is quite high. I would probably want it as low as maybe just 5, 4, or 8, or somewhere around that, because then I could do so much more without running into performance problems, and so either have the game run much lighter than it is now, or just have much more things in the game. But the way I designed it, it's quite important to have the 30 ticks per second. It would be quite a big rewrite now, due to like how the minor source updates and things like that. But yeah, a tick rate of 30 is quite high. For comparison, I think the tick rate of Minecraft is like 20. And I think like City Skylines, I think has a tick rate of like 4 or something in their car simulation, for example, to be able to have a lot of cars simulated at the same time without it being too expensive. Prepare, okay, yeah. And then on the logic thread, some of the render data is prepared here, just to make sure, just to make sure that it's done at the state where we're not currently updating it. Because if this was run on the render thread, then we could fetch data that is currently being written to, and then some things could be out of sync. That's what I did at first when I introduced the multi-threading stuff, and then I had issues with the moves stuttering forward or flickering a bit because it was a bit out of sync, and so it's run here, and we going through all the minors, check which ones are visible, and if it's not visible we just ignore it, and then we fetch all the data that's needed for rendering and add that to the render list, which is just holds an array of all the render data that's needed. That's what was used in the render minor functions. And the same goes for the minecarts, due to the same thing. And we also set the last logic update time in here for the interpolation thing. And also, yeah, and here I also have some locks, because if we're currently using the render data to render, then we don't want to write to it, because then if we write to it mid, then we would also have these issues. So have a lock for each render data type here that waits for it in case it's needed. And that's pretty much it. Yeah, and then it has a cell in here as well in case that's needed. So that's the whole logic thing. And in the logic thread, yeah, you can just go through here. Just set up all the memory arenas for the different tasks, and all these task memory arenas are no growth true, and that is so they are never. I just allocate the memory that's needed for the maximum amount of tasks that can be run at the same time up front, and that's basically because I didn't want to bother trying to fix like stray pointers. So when these are used for the task, I just send pointers to the memory allocated that holds the data, and if we were to reallocate and copy that data, those pointers would no longer be valid, and then it's best case scenario it crashes and lets you know it's wrong, or worst case there's still something that can be read and everything just goes to shit. So this no growth makes sure that if there's not enough room when we need to allocate stuff already in the arena, then it will just crash to let you know that there's a bug, that the memory arena is allocated too small. init task runner is down here. And then in the task threads, a number of threads are basically just the number of processors minus 1, but at least 2, so we can run the logic thread and the tasks on separate threads. So we can run more than one thing. So the logic update actually runs on even a separate thread. This could probably be optimized a little bit more. Maybe I'm using a bit too many threads for the task. I want to take a look at the whole thing at some point to see if there's any easy gains here. We'll see. That's the logic thing. Yeah, that's pretty much the whole overarching overview of the code in the game, and I'm not sure. Yeah, I don't think this. I'm not gonna go into more detail, at least in this stream, because it would take too much time. So it would have to be like specific things that people are interested in. If any of you that are currently watching have any questions, please write them in the chat. Otherwise, I think I'm pretty much done here for today. Maybe we'll do another one of these in case there are some more specific things that people are interested in. So if you're watching the VOD, you can comment on just comment on under here, and I could maybe if it's easy I can just answer it in text. Otherwise, I have it for consideration in future. Let's see. A question here. How much runway did you have before you quit to go full time in the dev? I had a runway that would, I think, would let me be able to do it for like 2 years. I think that was yeah. It would. I could cover my expenses for a little bit over 2 years with my saved money, and yeah, and then that ended up being enough with since Moose Miners has sold quite well, even though it's not selling as much anymore. So at least, so I have to release a game that sells quite well soon enough. We'll see if Moose Diver will be it. Yeah, and speaking of Moose Diver, it's releasing on Monday, and if yeah, let's see. This is the game, the Moose Diver game, and if you haven't wishlisted it, please go ahead and wishlist it and mark your calendar. Yeah, but yeah, if there's no other questions right now, I'm probably gonna end the stream here, and thanks everyone for watching. Bye bye.